Recording now.
Yeah. So I extend a very warm welcome to Dr. Punita Verma for giving the first lecture today. So I would like to introduce her again. Dr. Punita Verma is presently working as associate professor.
The voice is not clear.
Oh, sorry, sir. Is it clear?
मैम इको हो रहा है, शायद दो डिवाइसेस कनेक्टेड हैं.
अच्छा मेरा फोन पास नहीं रखा है. Is it okay now?
Yeah, this is better, ma'am, now.
So Dr. Punita Verma is presently working as associate professor in physics at Kalindi College, India. She has about 23 years of teaching experience and 25 years of research experience. Her field of specialization is accelerator-based experimental atomic physics. She was awarded. Please share the current slide. Need to please share the current slide. She was awarded the DAD service, German Academic Exchange Service Fellowship for doing PhD in Germany. Her PhD was awarded by Utrecht Leibniz University, Germany. She has been awarded Indian National Science Academy DMC program for the year. She has been involved in the guidance of PhD, postgraduate and undergraduate research projects, along with 13 students for undertaking and completing their dissertation or project of professor. She has been awarded the Teaching Excellence Award. It's an industry recognition award under the Innovation Research Council. She is a member of many non-scientific.
Ma'am, your voice is just not clear. Ma'am, your voice is not clear. So it's echoing. So I think I will just, because we have static students coming every day, I think such an introduction is sufficient. It's already there on the PPT also. So your voice is echoing. So, well, I am very well known to all the students who are present here. And they have already attended 2 lectures from me. So they know me well, and I think we can skip this portion. May I share the screen now?
Yeah, please, ma'am. Shall we start now?
Is my voice clear?
Yes, ma'am. The voice is clear. We have also shared the screen. Just a full screen view would help.
So okay.
Thank you.
Yeah. This is the slide which I used in one of my earlier lectures also. And this is just to remind you that while we move forward, these are the questions that must be kept in our mind. Probability, its theorems, independent, dependent, and mutually exclusive events. What are microstates? What are macrostates? What are the examples of macro and microstates for all the statistics? What is the meaning of degeneracy and its importance in the 3 statistics? What is phase space? What is the difference between position space, momentum space, and their amalgamation for the phase space? How do you represent phase space in Hamilton's representation of canonical coordinates? This is something which is not covered by every book of statistical mechanics. And for these, we must follow specialized books, as I've already told you. Entropy and thermodynamic probability, we have already reached that level where we have already covered all this. And Maxwell-Boltzmann distribution law, why Maxwell, what is the distribution? Which quantities are distributed? Is it same or is it different from kinetic theory of gases, Maxwell-Boltzmann distribution law? It is same, the law is same. How is it different? It is the perspective and the attitude regarding the particular system that we are studying that is different. Partition function, what is it? Why is it required? Is something partitioned? If yes, then amongst which parameters? And thermodynamic functions of an ideal gas. Which gas is being considered? Which gas is called as an ideal gas? And why do we have to calculate thermodynamic functions? Well, we are somewhere having covered a lot of these points within the past 4 or 5 lectures that you already got on statistical mechanics. And then you remember this slide where I have given in details how in order to learn and grasp statistical mechanics from the lower level, that is the graduation level to post-graduation level, how you must keep on increasing your knowledge with these subjects and with these books which are mentioned here like a ladder. So you start with Beiser, you study Garg Bansal and Ghosh, Loknathan, then Guha, then Sahasrivastav, and then further you have to go to Raif and then Patreya and so on and so forth. This is just to remind you and for any student who has joined late with us. So this is where I left yesterday, and so I will continue from here. We had reached a conclusion that the Bose-Einstein and the Fermi-Dirac distribution functions are represented by these two functions, and with the other two speakers in statistical mechanics, we have reiteratively told you about these functions, and some numericals have also been done. So the Bose-Einstein distribution function is given as shown in the first equation, that is equation number 9.26. So 1 by exponential to the power of alpha, exponential to the power of e by kt minus 1. And the probability for a fermion, where I stopped yesterday, comes out to be the function for Fd is 1 by e to the power alpha, e to the power e by kt plus 1. What is alpha? Alpha is a function of the properties of a particular system. It may be a function of P. As we deal with different systems, both for Bose-Einstein and for Fermi-Dirac cases, we shall be dwelling in detail of alpha and what is the value of alpha and why and so on and so forth. Presently, we are understanding the general framework of statistical mechanics and grasping the very basic concepts, after which we go to the second level of delving deep into each and every statistics and its applications in detail. So we see that in the Bose-Einstein distribution function and the Fermi-Dirac distribution function, the only variation which is visible is of -1 in the denominator for 9.26 equation and of +1 in the denominator for the Fermi-Dirac distribution function. Well, if we just look at these two equations, 9.26 and 9.27, only from the point of view of pure mathematics, then what do we conclude? It's an exponential function. There is a parameter e by kt -1 and +1, and we all know how the exponential functions behave and what is their expansion. This Maxwell-Boltzmann distribution function, which has been written in the lower part of the slide, is just to remind us that this was the equation for Maxwell-Boltzmann distribution. Now the term -1, it signifies a very increased probability that any energy state is occupied multiply by bosons. Some of you have already completed post-graduation, and some of you are going to complete graduation. Nevertheless, each of you is aware of the different behavior of Bose-Einstein statistics and the Fermi-Dirac statistics, the bosons and the fermions. The term -1 signifies the increased probability that any energy state is occupied multiply by bosons. And in my last lecture yesterday, I had explained how the overlap of the wave functions signifying the bosons led to this kind of conclusion. And the term +1 for FD distribution is a consequence of the uncertainty principle. The Fermi-Dirac distribution is followed by fermions, and they must follow the Pauli exclusion principle. They must follow the uncertainty principle. The Pauli exclusion principle does not allow another fermion to settle or sit into the same state as the first one. It must have some aspect which is different, irrespective of the values of alpha. So it's not A, it's alpha, E and T. The values of Fe can never be greater than 1. Can never be greater than 1. I will go back to the slides and please look at the two equations once again. Bose-Einstein statistics with its -1 factor and Fermi-Dirac statistics with the +1 factor. The Fe can never be greater than 1. Okay. And the Boltzmann distribution is also written in the last portion of this slide. In both cases, when E is very much greater than kT, the energy of the system about which you are concerned, if it is greater than kT, that means if it is greater than T, because K is just a Boltzmann constant, the two functions start approaching Maxwell-Boltzmann distribution function. They start approaching Maxwell-Boltzmann distribution function, and by pure application of mathematics, one can see that immediately. Now what happens? At any given ratio of E by KT, it is absolutely clear from the three functions itself, one with -1, the other one with +1 for FD, that the function for Bose-Einstein distribution will be always greater than the function for Maxwell-Boltzmann distribution. I repeat, the function for Bose-Einstein distribution function, that is the one which I showed in the first equation having a -1, is always greater than the function for Maxwell-Boltzmann distribution, and FD is always smaller. Now let us look at the comparison of the three statistics which I also showed yesterday for a short time. So one is an exponential function, the other one has a -1 and a +1 factor. So from pure mathematics itself, we can see very clearly from this diagram that if we plot this distribution function Fe with respect to the energy about this of the system which we are concerned with, and if we choose the x-axis to be in terms of kT, then 1 kT, 2 kT, 3 kT, and 4 kT, we will find that the three functions, if plotted, follow this behavior. So comparison of these three distribution functions for the same value of alpha. What do we see? The Bose-Einstein is larger, Maxwell-Boltzmann comes in between. It's a pure exponential function, and Fermi-Dirac is less. The variation in the three statistics occurs for energies and hence for temperatures which are in the major part below KT. If you look at the graph and look at the x-axis, then for temperatures below KT, for energy less than KT, you have maximum deviation. And as the energy increases from KT to KT and further, these three statistics start approaching the same kind of behavior. And on the beyond 4 KT, it is just it's just similar, and we cannot differentiate between one statistics and another. So the remarkable change in the statistics occurs at low temperatures. These functions give the probability of occupancy of a state of energy E at this absolute temperature T. And that exactly was our purpose, as I explained to you yesterday, that in statistical mechanics, we are bothered to find out whether at a particular temperature T, for a particular energy E given to a system, having this total energy E as a constant and the number of particles allotted to the system as a constant, with these two constraints in mind, we want to find out how to distribute the energy which is available to the system amongst the various energy states or level of the system, and that distribution function is this F which we are talking about. So just a second, I'm sorry, just a second. I'm having a problem for moving my slides. Just give me 1 minute. There is a time lag or network problem. Just 1 minute.
मैम वो फुल स्क्रीन को वापस मिनिमाइज वो करके एस्केप करके और फिर वी कैन डू दैट.
The slide is not moving, so just 1 second. It just happens sometimes, not always. So meanwhile, if the students want to ask any question, they can just put it up into the question and answer box only. Somebody raised a hand. Dr. Neetu, can you please look at it? So I'll stop sharing and start sharing again. I don't know, the slides have got stuck and they're not moving. I'll just stop share and start share again.
Sure.
Yeah. Yeah, there was some network problem. So
Ma'am, would you like to take the question in the end, or there
no,
are
in the
in
in the
between
end,
questions?
in the end, and I also answer them on mail and WhatsApp, whatever they are asking me. It's not a problem.
Sure. Sure.
So the Fermi-Dirac distribution, I've written again, FFD as a function of energy is equal to 1 by e to the power alpha e to the power e by kT plus 1. And from this equation, we can see that this function becomes half for a special energy. It is special because it has got a special designation and a special importance in physics. So from this equation, if we want a function, this function to have the value of half, it will occur when we will have EF equal to minus alpha KT. So if we substitute E to the EF is equal to minus alpha KT, we'll get a value of half, or we can, if we put a function to be equal to half, we get the energy to be equal to minus alpha KT. What is this energy? This energy is called the Fermi energy, and it is a very important quantity in a system of fermions. The importance of this Fermi energy we shall see progressively as we talk about different systems which are valid for fermions and which obey Fermi-Dirac statistics, especially the behavior of electron gas in a metal. So in the first class, there was a question that how can an electron be considered as a gas in a metal? So it is like this. The metal conductivity was properly explained only with the help of Fermi-Dirac statistics. The conductivity of metals was completely explained by the application of Fermi-Dirac statistics to metal conductivity. What conducts who conducts the electricity in a metal? It is the electrons. There are free electrons which are available in any lattice of any metal that you pick up from the periodic table. And these free electrons move around the lattice almost like free electrons, and hence can be considered as an electron gas. And that is why the word electron gas. In terms of this Fermi energy EF, the Fermi-Dirac distribution can be re-represented or can be rewritten in the form of equation 9.29. What have I done? It is just E minus EF, nothing else, by KT, and plus 1 remains as it is. Now, this is the most general Fermi-Dirac distribution, which you will find in the same structure and in the same manner in most of the books which deal with these statistics from the graduate level. Further, the distribution obviously remains the same. However, we will try to understand it through different perspectives as I shall go on in the next lectures from tomorrow. So now let us understand and appreciate the significance of the Fermi energy as if we are trying to understand only a portion of it. Again, it will be dealt in detail, as I said, when I will deal with conductivity of electron gases in Mech. But to appreciate the significance of this Fermi energy, let us consider a system of fermions. What are fermions? Fermions are those particles which are obeying Fermi-Dirac statistics, and their spin angular momentum is a half integral multiple of h cross. What is h cross? H cross is h divided by 2 pi. So the system of fermions at t is equal to 0, and investigate how are the states occupied. In my last class, I have explained that you can take any example, a very simple example of 4 or 5 energy levels and some particles, and try to distribute them amongst those energy levels. And then in the end, every possible macro state will tell you how much is as a state occupied. So whether there are 3 particles in one energy state, whether there are 2 particles in another energy state, whether there is 1 particle in an energy state, or there is no particle in that energy. So at t is equal to 0, we consider a system of fermions, and we remember that the uncertainty principle and the Pauli exclusion principle must be obeyed by these fermions. So for energies less than this Fermi energy, which is called EF here, and greater than EF, we can find out like this. So we use the function which is in front of you for t is equal to 0, 2 energy cases. Once the energy is less than Fermi energy, E less than EF, and for second, energy E is greater than EF. If we do that, then very simple basic mathematics gives the answer that for energies less than the Fermi energy, the distribution function is equal to 1. And For energies greater than Fermi energy, the distribution function is 0. Okay. So let us look at the first figure on the left-hand side of the slide, top left corner, marked as A, where the function Fe has been plotted with respect to E, and the Fermi energy has been designated as EF right in the middle. And what we find that the function is 1 and till EF, and after that it is 0. Similarly, we can look at now figure number B, which is the middle figure on left hand side of the slide, and the function Fe plotted against E, the energy of the system. EF is marked, and at this point we can see that if the temperature T is equal to 0.1 EF by K, then how the function changes. Further, increase the temperature, and what do we observe? We observe in the third figure at the top left, at the bottom left corner of the slide, marked as C, we see that the Fe function changes from a square in the A part to, or a rectangle in the A part, to a sloping line with a negative slope. What does it signify? It is obviously clear that this Fermi energy is an energy value which is bringing a change in the behavior. At Fermi energy, T is equal to 0, all the states below T is equal to 0, all the states below EF are completely occupied. If we increase the temperature, then some states just below Fermi energy are less occupied, and some states just above Fermi energy are occupied, although to a smaller extent. The part B figure. Looking at part number C, if we increase the temperature, then this is the indication of the sloping line which we observe in this particular figure. So the Fermi-Dirac statistics of this particular figure and the one which is shown below, this is just a small portion, it's not a complete portion. So this sloping line with a negative slope is just a part of that particular function which I just showed now. So distribution function for fermions at 3 different temperatures, T is equal to 0, low temperature and higher temperature, and we see how the distribution function changes with respect to temperature, and thus makes us understand that at the Fermi energy, if the temperature increases, then the number of particles occupying particular states will increase towards higher values with higher energy, or you can say with higher temperature, because energy is definitely linked to temperature, as we know very well. Fine. The figure on the left remains the same, and we try to just think and ponder upon what does it signify. So at absolute 0, all energy states are occupied, and there are no states occupied above EF. If you consider n number of fermions, as I have said, take the total number of system particles as capital N, we can calculate the Fermi energy by filling up all its energy states with the n particles in order of increasing energy. However, while filling the different energy states up till the Fermi energy, we have not to forget that the Pauli exclusion principle has to be valid, and hence in one state, only one type of particle with a particular energy and spin shall be allowed to fit in. And if there is another particle, then it will have to go to another state. So the highest state to be occupied will be then E is equal to EF, and this calculation will be made for the electrons in the metal later when we will take up that in detail. Now for temperature increased above T is equal to 0, and if KT is still smaller than EF, fermions will leave the states just below EF and move into states just above it. And that's the sloping figure which we find in figure number B. At still higher temperatures, fermions from even the lowest state will begin to be excited to the higher ones, and FD0 will drop below 1. So in these circumstances, FD assumes a shape, as I've already discussed in the previous slide, and this corresponds to figure number C. So the properties of the 3 distribution functions are going to be summarized in the next table, and it is necessary for us to remember that to find the actual number of particles with an energy E, the function Fe must be multiplied by the number of states GE having this energy, which is also called as degeneracy. And if I just remind you, just in the beginning of this lecture, I said reiteratively that degeneracy, that is the number of states having the same energy, must be kept in mind for each and every system and application of statistics that we study in this particular subject. So let us now recapitulate and see what have we understood about the three statistics before we start applying these three statistics to the different cases. So Maxwell, Boltzmann, Bose-Einstein, and Fermi-Dirac statistics. This applies to a system of identical distinguishable particles. Please note, it is identical. However, we are writing distinguishable. To many students, this is a source of confusion. If it is identical, how are you distinguishing it? And if it is distinguishable, then how come it is identical? This particular word bothers many students, and I remember myself as a student having a great confusion regarding this. And the answer to whether it is identical and distinguishable lies in the application of quantum mechanics to the systems where you associate a particular wave packet to a particular particle following wave particle duality, and you remember that in the case of Maxwell-Boltzmann statistics applicable to ideal gases, the wave functions do not overlap, or rather overlap to a very negligible order. And hence, although the gas molecules in an atomic gas or in a molecular gas are identical, they are in these statistics considered as distinguishable. However, when we move to quantum statistics, that is Bose-Einstein and Fermi-Dirac statistics, we have identical and indistinguishable particles, and we know the examples of these two statistics following particles. So we know fermions. The simplest one known to us is electron. It's a fermion. And we have bosons. Say they do not, the Bose-Einstein statistics particles, the bosons will not obey the exclusion principle. They have no problem. They are the friendly particles. They allow the other particles to settle into the same energy state in which they are. The probability that one boson is sitting in a particular energy state leads to the idea that more and more particles will enter that state. However, the Fermi-Dirac statistics will obey the Pauli exclusion principle, and in one particular state, only one type of particle with a particular spin shall be allowed to enter. The category of particles we know is classical, bosons or fermions, and properties of particles is any spin. Particles are far apart, and so the wave functions do not overlap. And Bose-Einstein, the spin is integral multiple of H cross. Integral multiple of H cross is the value for bosons having spin angular momentum either 0 or 1 H cross or 2 H cross and 3 H cross and so on. The wave functions here are symmetric. So if you interchange the particle labels, the wave function remains the same. The total superposed wave function remains the same. However, for Fermi-Dirac statistics, followed by fermions, the spin angular momentum is half integral multiple of H cross. And the wave functions after superposition for all the particles of a system will be antisymmetric if you interchange the particle labels. What are the examples? The examples are, you can consider molecules of a gas in a Maxwell-Boltzmann statistics. You can consider an atomic gas also. In Bose-Einstein, we apply Bose-Einstein statistics to the photons in a cavity, to the phonons in a solid, and to liquid helium at very low temperatures only. So all these three cases which are mentioned here and many more will be covered in the following lectures. The Fermi-Dirac statistics followed by fermions are applied to free electrons in a metal and the electrons in a star. So we understand the white dwarf stars and so on because of the application of Fermi-Dirac statistics. So stars whose atoms have collapsed, that is a white dwarf star. And the distribution function I've already talked in detail about, and so that's not to be discussed again. I suppose it's very clear to us. And the properties of distribution, there is no limit to the number of particles per state. There is no limit to the number of particles per state. In yesterday's example, where I had taken 5 energy levels, E1, E2, E3, E4, E5, 5 energy levels, and available to a system of particles denoted by 3 red balls, 2 blue balls, 2 green balls, and 2 yellow balls, there is no limit to the number of particles that you can put into a particular state. But this is not the case for the other two statistics equally. There is a difference. There is definitely no limit to the number of particles that can settle into a particular state, which are the particular state for Bose-Einstein systems or for bosons, more particles per state than MFB at lower energies. So if you compare the two distributions at low energies, then the number of particles in the Bose-Einstein case can be greater at lower energies. And this is the very base and the very reason why we have Bose-Einstein condensates. And if you increase the energy, this value of FBE will approach MB function. So when we understand statistical mechanics, we start getting the feeling that it would have been much better to start with quantum statistics and arrive at classical statistical mechanics as a special case of quantum statistical mechanics. But for pedagogical reasons and for historical reasons, we have to first study classical, because quantum is introduced much later to us in any field of physics study. So by this sentence itself and by this conclusion itself, we are reminded of the fact that Bose-Einstein statistics in special cases at high energies will lead to Maxwell-Boltzmann statistics. And in this inference itself is the inference that when we study statistical mechanics from 3 different point of views, classical and quantum, and within quantum, Bose as well as Fermi-Dirac statistics, then we must be able to derive all the thermodynamic quantities and their relations through statistical mechanics. So we calculate a particular statistics function. We have calculated, we have seen to a certain extent the function distributions for all the 3 statistics, and now at high temperatures we are now capable of applying these functions, use high temperatures and calculate or arrive at or deduce the 8 thermodynamic quantities which are the basis of thermodynamics: pressure, volume, temperature, internal energy, Helmholtz free energy, Gibbs free energy, and entropy. And the bridge, as I said, is the entropy, which is bridging thermodynamics to statistical mechanics by the beautiful equation of Boltzmann relation. S is equal to K ln W. So in my last 2 lectures, what have I been pointing out? I have been pointing on the fact that the first thing that we have to calculate is the most probable macrostate W. And for the most probable macrostate W, S is equal to K ln W, we must understand how to distribute the particular number of particles in the particular number of energy levels available to my isolated system. To my isolated thermodynamic system, which has already reached equilibrium, I want to first distribute my total number of particles, which is constant amongst total energy levels which are available for that particular system. And when I distribute, I must find out all possible combinations, permutations and combinations by which I can do that. What is the difference between permutation and combination? I'm sure you know. Permutation means that AB, if there are 2 particles A and B, then AB is not equal to BA. Permutation means if there are 2 particles A and B, then AB is not equal to BA. That means the location and the position of the particle designated here as A and B is important. So the number of permutations for any 2 particles to be distributed amongst some energy level, say 4 or 5 in number, the permutations will be large. However, if I want to see the combination, that's the arrangement without taking care of the fact whether AB is written or BA is written. So in combinations, AB is equal to BA. And you all are aware of how to calculate permutation and combination from your school level mathematics. Now to the end, the Fermi-Dirac, never more than 1 particle per state. So why never more than one particle per state? Never more than one particle per state, because they must follow the uncertainty principle and the Pauli exclusion principle. So there are fewer particles per state. There are fewer particles per state as compared to Maxwell-Boltzmann distribution, even when you go to even when you approach low energies. However, again at high energies, as we saw in the previous graph, the FMB, that is the function for Maxwell-Boltzmann statistics, is approached by even Fermi-Dirac statistics. And that is the and that's the reason why at higher temperatures, the specific heat of metals and such like phenomena can be explained by the normal Maxwell-Boltzmann distribution. However, if we reduce the temperature, we must apply the quantum statistics of either Fermi-Dirac or Bose-Einstein, depending upon our system, whether the particles in consideration are either bosons or fermions. So at this point, am I audible?
Yes, ma'am. Perfectly.
I'm audible. So I will just have a look at, before I move further, I would just have a look at this one, two questions. What is the consequence of the uncertainty principle? Okay, we remember the question. Okay, these questions have to be, so I must mention that all the questions the students are asking somehow indicate that their basics of statistical mechanics is not clear so far. So that's the reason why these classes are being simultaneously held along with numerical practice and numerical approach. So all these 4, 5, 6 questions, I've read them. Please wait for 2 more classes and all your questions will be answered, because I'm going to cover them in the coming lecture tomorrow also from a different way. So I will touch upon this all over again. So I just now move a little bit further and show you a different perspective of how to deal with a particular classical system. Not this way, but slightly different. However, available in all standard texts that are followed all over the world to understand statistical mechanics. So, again, there is a problem with this slide share. I don't know, for some reason it gets stuck. I don't know why. I'll have to stop share and start again quickly.
Yes, ma'am. Now this is shared again.
Yeah, there is some network issue. Doesn't seem to be zero, but it just gets stuck. I don't know why. Just a second, I'm back there. Yes. So, yeah, yeah. So we are at classical statistical mechanics, and statistical distributions are of 3 types, 3 kinds. We have seen a comparison of them. They have seen the different functions, and we have seen how they compare with each other. They're applicable on whom, and what is the role of temperature, what is Fermi energy, and so on. I've also spoken about phase space, as also the other teachers, and now the Hamilton's equations. Before we go to this approach, which is dealing of classical statistical mechanics through Hamilton's equations, the 4 or 5 points that I've written on this slide is just to remind you that this is the other perspective by which the classical statistical mechanics is dealt with in books like Huang, in Rife, in Patria, and in Mandel, and all those which are coming after 4 or 5 ladders of my book ladder. So, what is the aim of statistical mechanics? Again, it should be clear to us. The aim of statistical mechanics is to derive all the equilibrium properties of a macroscopic molecular system. Okay, from where? From the laws of molecular dynamics, and also to arrive at all thermodynamic relations, as I mentioned just now. It is also aimed at to calculate the most probable distribution. the most probable distribution of the particles in the available energy levels is the distribution which comes automatically at equilibrium. So if there is equilibrium, then that distribution is called the most probable distribution. Or if you notice and understand and are sure about the most probable distribution, then it is very obvious that the most probable distribution is occurring at equilibrium. So the method of most probable distribution to discuss the equilibrium solution of not only of dilute gas, but also for any macroscopic system, This generalization is called classical statistical mechanics. Now, consider any classical system. You can consider a classical system of a gas of molecules. Obviously, the number of molecules in a particular gas is very large, let's say 10 to the power 23. And the volume is also very large. Say, if you're considering molecular volumes, that is also very large. Now, these are enormously large numbers, and therefore, it will be obviously convenient to consider the system in the limit that n is tending to a very large number, infinity, and v is tending also to a very large value. It is tending towards infinity, and then v by n is equal to small v, which is called the specific volume. And this specific volume is a given some finite number. Now, the system has to be regarded as isolated in the sense that energy is a constant of motion. The energy, as I said from the very first lecture, must be a constant of motion. It is constant for a particular system. It does not change. Now, this is kind of a little bit of idealism, because it is not easy to have a system whose energy is absolutely constant in many cases. Okay, then in that case, all the interactions with the external world for taking an isolated system is also very difficult. So the measurements, we know that if we try to measure any quantity for any system, any parameter, then this measuring the interaction procedure, the procedure to measure the interaction will itself provide energy to the system or will disturb the system. So it is isolated system, not having any perturbation and having total energy as absolute perfect constant is purely an idealization. However, considering this idealization and arriving at different classical statistics inferences leads us to almost accurate results. So now we have already heard a lot about the Hamilton's equations of motion through our classes of classical dynamics. And here we have to consider that any state of the system is completely and uniquely defined by 3n number of canonical coordinates. Which are these 3n number of canonical coordinates? Which are these 3n number of canonical coordinates? I'm saying 3 multiplied by capital N. 3 multiplied by capital N, where N is the total number of molecules available to the system. 3n, why? Because, as I mentioned yesterday also, if you have any system and if you want to find out its position, you can denote it as q1, q2, and so on. So you can go for the 3 different dimensions to q3n. That means position coordinates for the 3nth particle also. And additionally, you have 3n number of canonical momentum. Momenta, as I explained, momentum is mass into velocity, we know, and in the phase space, we need both the position as well as the momentum. The position space and the momentum space combined together is called the phase space for a particular system. And we in statistical mechanics are bothered about the phase space of a statistical system. In the top of the slide, I've just written what I said, that we must derive all the equilibrium properties of a macroscopic system. We must derive the general laws, also the specific thermodynamic functions of the system, like entropy, internal energy, thermal energy, and so on. The Maxwell relation is extremely simple, and the method of most probable distribution leads to the equilibrium of dilute gas or any microscopic system. Now, let us look at these few equations. I will be able to explain one or two right now and the rest again in the next class. So we are aware of the canonical equations of motion. This H here is the Hamiltonian H, which is dependent upon P comma Q. What is P? P is the momentum and Q is the coordinate, position coordinate. So we know these two very famous equations of motion, that is del H, del Pi, where H is a function of momentum and position, is equal to Qi dot, and del H del Qi, function of P and Q, is equal to minus Pi dot, where dot simply means that it's a derivative of this quantity, that is Pi. So it is then very convenient that we think of the tau space of the system, which is 6n dimensional. Why 6n? 3n for position and 3n for momentum. Now suppose I have constructed such a 6n dimensional tau space of the system. You can call it tau, you can call something else. Obviously the name does not matter. This 6n dimensional space, which I have constructed out of position momentum coordinates, here if I want to represent the state of the system, then how do I do it? Suppose I represent the state of the system in this tau space, then it is very convenient to represent it. How? I'm just focusing. Let us first understand what do you mean by state of the system. This word appears everywhere in statistical mechanics, and to the mind of a student, the state of the system remains unclear for many cases, and sometimes even after post-graduation. What do you mean by the state of the system? You see, we have heard of the word state of the system in thermodynamics. And when we say, what is the state of the system? We say the state of the system can be completely and uniquely be described by the 8 quantities: pressure, volume, temperature, entropy, internal energy, Helmholtz free energy, Gibbs free energy. So these 8 quantities completely describe the thermodynamic state of a system. Is it sufficient to define the state of the system only by these thermodynamic quantities? No, in statistical mechanics. In statistical mechanics, we must understand that the distribution of the particles in the various energy levels, which must be the most probable distribution, defines the state of the system. So the system, suppose it is having 2 energy levels, it has got 2 particles, then the state of the system will be 1 particle in each state. So one particle in the first state, second particle in the second state, or both the particles in the first state, or both the particles in the second state. These are the 3 possible states. And if it happens that both the particles in the lower state is the most probable distribution and occurs at equilibrium, then this is the state of the system we are talking about in statistical mechanics. And this, when represented in a 6n dimensional state of the system, will be a point. So suppose we know the state of the system. We have seen all the 8 parameters of thermodynamics. We have seen the distribution. It has reached equilibrium. We have reached the different distributions. And we know that this is the most probable distribution. Once it is done, our state is defined. And that definition of the state will be designated by a single point in the tau space. Now the locus of all the points in the tau space which satisfy the equation H is equal to E will define a particular surface. I'm repeating that all the points in this 6n dimensional space will lie on a particular surface of energy where H is equal to E. Why H should be equal to E? H is denoting position P and momentum Q, and these two together define the energy E. So the surface of energy with H is equal to E is the locus of all points in the tau space that satisfy just one equation, H is equal to E. Now, if the state of the system evolves, that means I change the energy, if I now change the state of the system through a different distribution, then the state of the system according to time will be tracing out a curve in the tau space. We'll be tracing out a curve in the tau space. And now, if we look at this path, it always is the same energy surface. Why same? Because as I said, that the energy remains constant and H is equal to E defines the energy surface. This energy surface has all the points in the tau space that satisfy this equation. So now the question is, what is thermodynamics bothered about? The question is, what does thermodynamics bother about, and what is the focus of statistical mechanics here? The focus of statistical mechanics is that we are not bothered about what a particular particle of the system is doing in a particular instant or in a particular situation. We are only bothered to find out whether the system as a whole, which system? Isolated. The system as a whole, how is it behaving? Now there are two ways how to deal with this. There are two distinct ways. Either I can say, yes, this is my system. What is its state now? Its state is this, where in 6n dimensional space. I note it and I put a point in this 6n dimensional space. Next, I again note the state of the system, again do the same thing. I will get a curved path and this will lie on an energy surface. This part is clear. Or I can introduce the quantity of ensemble, which is nothing else but a mental picture of such a collection of systems. Which collection of systems? The same system is imaginarily copied into several number. So I have one system and I imagine that I have made a mental copy of this system. I've made a mental copy of this system. Then I again make a mental copy of this system. The question is, why am I making copies? Why am I making mental copies? I'm making a mental copy of the system because here its state is different. Here its state is different. So the single system is imaginarily in imagination thought of as a collection of systems, and it is this collection of systems which is called as an ensemble. It is this mental picture of a collection of systems where all the individual constituents are nothing else but copies of the original system. What is the difference? They are copies, yes, but their state is different. Why is their state different? Because their distribution of number of particles in the energy levels is different. Because the way you have distributed the particles amongst the energy levels available to the system has now differed. So suppose if time is equal to t is equal to 0, I have a distribution, and time is equal to t is equal to t1, I have a distribution. At time t is equal to t2, I have a distribution. And instead of taking the same system again and again, I say, yes, I have 100 copies, I have 100 states, and now this is an ensemble that I have. This is an ensemble that I have. So obviously I can say that this distribution of points in the 6n dimensional space, this distribution of points is telling me nothing else but the different states of the system. States of the system means distribution of the system. Whose distribution? Particles distribution. Distribution where? In the energy levels of the system. This whole thing can then be represented by a density function denoted by rho in equation number 7.4. Can be denoted by a density function rho. What does rho depend upon? What does rho depend upon? Equation 7.4, del rho del t is what I can see. Rho depends upon obviously position, obviously momentum, and additionally it depends upon t, the time. T, the time. So all the points contained in any particular unit volume within this 6n dimensional space is denoted by rho, which is a function of pressure, of momentum, of coordinate, and of temperature. So this concept of ensemble means collection of mental copies of the same system. Now, for 1 second, we have to stop and ask ourselves, what if I have a collection of systems systems, plural, more than one. I have a system, and this system I've made a mental copy. Second, I have a system which is in itself a collection of, say, 5 systems. Then my ensemble is now not just a mental copy of this system, but a mental copy of all the 5 constituent systems that are within the first system. I'm repeating, we take a system, it has got particles. Very good. We have to distribute these particles, n number of particles in E1, E2, E3 energy levels. Total energy N is, total energy E is constant, total N is constant. Everything is crystal clear till now. The complication starts when the system itself is not a system consisting of number of particles, but it is a system which consists of a collection of systems. If it is a collection of systems, then when I make a mental copy and call it an ensemble, I've actually made a mental copy of all the 5 systems that are within the first system itself. So it's like, when you copy, you make a copy of its ingredients also. When you copy, you make a copy of the ingredients also. So that is the definition and understanding which we must have when we are talking about ensemble. And this approach of starting and understanding classical statistical mechanics is really the proper approach and is available in all the textbooks that we refer in any course of graduate or postgraduate study. So this concept of ensemble and density function is then further manifested in the Liverlees theorem, which is there in equation number 7.4, visible as second equation on this slide. So del rho del t is a sum, del rho del t, that means time derivative of rho, the density function. Whose density function? The density function of that ensemble dependent upon P, Q and T. T is time here, plus a summation over I is equal to 1 to 3n. Why 3n? Because each quantity, whether it is momentum or position, P or Q, both are 3n in number. You have 3n canonical coordinates and you have 3n canonical momentum. So summation over I is equal to 1 to 3n, and then within the bracket one can see that del rho del qi del h del pi minus del h del qi del rho del pi is equal to 0. This continuity equation we are very much aware of. We have studied continuity equation, we have studied Liverlees theorem in other fields of physics also, and it is now valid and applicable to classical statistical mechanics also. Now, what is it that we must understand out of this Liverlees theorem? Geometrically, it simply means that the distribution of points in the 6n dimensional space, it moves like an incompressible fluid. I repeat, geometrically, this Liverlees theorem simply means that the distribution of points, what are points? The points are the states of the system. Where? In the 6n dimensional space. What is the name of the 6n dimensional space? It is the tau space. So tau space is the 6n dimensional space in which each point which we have put as a mark there is denoting the state of the system. And geometrically, this equation means that this distribution of points in this tau space, which is 6n dimensional in nature, it moves like an incompressible fluid, like a swarm of bees, right? So we have to now think of which kind of ensembles we must deal with. In yesterday's lecture also, and in Dr. Sanjay's lecture also, ensemble were discussed upon, and some of the students could not relate themselves to this concept of tau space, the drawing of a path, the connection with H is equal to E energy surface. So Hamilton's equations, H is equal to E is the surface on which this particular path traveled by this ensemble of particles lies. If you will change the energy of the system, H is equal to E equation will change, and hence there will be a new surface. There will be a new surface, and on this new surface, the points which will be marked will be denoting that particular energy. So we restrict our considerations to only those ensembles whose density function does not explicitly depend on time. This is an extremely important base of statistical mechanics and must be kept in mind whenever we are observing any natural phenomena at the atomic or the subatomic or at the macroscopic level. Time is definitely a factor. However, when we are dealing with classical statistical mechanics, we're dealing with ensembles where the time dependence is not considered. So we say that rho PQ is rho dash H PQ, where rho dash is a given function of H. It follows immediately that the second term on the left-hand side of equation number 7.4 is identically equal to 0. And hence, del del T of rho, which is a function of P and Q, is equal to 0, as we can see in the final equation. So I'm just repeating. Liverly's theorem is evident in equation number 7.4. Here the density is the density, that is density of the representative points. Once again, what are they representing? They're representing the state of the system. The system state is represented by its most probable distribution for a particular case of distribution. And therefore, del T of rho PQ will be equal to 0, because in equation number 7.4, the first term is considered to be 0, the second term has to be 0. And now we must stop for a second and think about also the the theorem or the postulate of equal a priori probability. The postulate of equal a priori probability. That means prior to the occurrence of an event, the probability that you can have this particle in the first level, second particle in the second level, or the second particle in the first level itself is equal probability. Prior to the performing of an experiment or prior to the occurrence of any event which is at either macroscopic or at the microscopic level, the probability for occupying a particular energy level is always the same. So it is equally likely that any system can be in this state or that state. All are equally probable. And if you keep this in mind, then the application of statistical mechanics to various cases, which we shall do subsequently in the coming lectures, becomes very, very clear. And clear not only in concept, but also in understanding. So this postulate, what does it imply? What does it mean for us? It means that in thermodynamic equilibrium, the system under consideration is a member of an ensemble. And which ensemble is it? It is the microcanonical ensemble. In all studies of statistical mechanics, you have to understand three kinds of ensembles: microcanonical, canonical, and grand canonical ensemble. Clarity in the understanding of these three kinds of ensembles is extremely important for understanding any portion of statistical mechanics. So this density function rho, which is a function of momentum P and position Q, it is equal to 1. It is equal to 1 if the energy of the system is less than H, the Hamiltonian, which depends upon P and Q. And H is less than E plus delta. What is E plus delta? It is very simple to understand. If you're considering an energy surface E, then if the energy is augmented by a small quantity delta E, then there will be another energy surface E plus delta E, and the Hamiltonian dependent upon P and Q must lie between E and E plus delta E. E and E plus delta E. And rho, the density function, describing or representing the various points in the 6n dimensional tau space must be equal to 1. What does it mean? It means that the state, the system is in that particular state. Which state? Which state? A state which lies between E and E plus delta E. A state, the system is lying in that state whose energy is equal to E and E plus delta E. And this is for the cases where you allow a very small augmenting of the energy surface by the amount delta E. And the probability of finding the system is that rho must be equal to 1 if the Hamiltonian H is lying between E and E plus delta E. Otherwise, it's 0. Otherwise, it's 0. So I think I have. So I would like to stop here for today. And once again to remind you, Dr. Aditya has not joined us yet, right? Okay. So what did I try to cover today? So this was the second slide which I showed in my lecture yesterday, day before yesterday. The classical entropy expression, how was it different or similar to that of thermodynamics? This we have dealt with, and we would be dealing with the numericals in this. And this particular portion, so tomorrow I would be starting from where I've ended today. I think by today we have understood what is classical statistical mechanics, what is ensemble, what is the importance of Hamilton's equations of motion here, and the canonical coordinates, position and momenta. And then how we can use Liouville's theorem to understand the flow of density points in tau space. What is the difference between canonical, microcanonical and grand canonical ensemble will come later. A part was already covered by Dr. Sanjay. Further, using these concepts, we will talk about entropy in a system of two gases before and after mixing, the Gibbs paradox, Boltzmann counting, and Sackett-Tetrode equation. For those students who are interested in understanding the subject completely within this time duration that we are having lectures for you, are advised to read or suggested to read over these topics from their relevant book of study and from the books that we are continuously giving to you. So with these words, I will now stop sharing for the present. Right?
Thank you, ma'am. This was such thorough and beautiful presentation. The PPT was so nice, and there were some questions. So participants, we have already conveyed you. We'll take them up through email also, and we'll join you in the next session as soon as the speaker joins us.
Yeah. So Dr. Neetu, I request you to kindly stop the recording for the present.
Surely, yeah, ma'am.
Yeah. So
yes,
it's been almost 1 hour, 10 minutes. So I'm just reading through the questions. The students